lab.
I didn't do it either.
Yeah, the department recommended not bothering with it.
Yeah.
They said the only thing that matters is your advisory reads.
Well, my department thought it was a good idea because you can get more
But it
publications that
we
way.
had hopefully.
I was able to do a lot more projects that way.
Yeah, exactly, and that was really nice.
Apparently,
That was
degrees were considered consolation prizes.
Oh, really?
Because you failed out your PhD program.
Got the air.
At least at MSU at the time. They said you can't really do anything more with the masters than you can with the bachelor's. So it's different in the land management. The masters is wildlife and all that stuff. So you have to get masters.
Figure out how these campers all super excited.
Oh, good.
Yeah.
Run across the hall.
It's been a while since she was graduated.
He looks under them.
It's been more than 5 years since Katie was here.
What's up, sir?
This Katie?
Right it up.
Yeah, more than 5 years.
I had not quite the same experience with your parents. Like, we have this data. We think it means something. We don't know how to say
When I
it.
see like Josh.
Please do that for us. And so 9 months later, I came back and was like, I did it.
Yeah, yeah.
And that's the first.
I just don't ever
And
recognize.
that's all you're doing.
No, that was all my, that's my kids.
Well, yeah.
But that was my skill. Yeah, my master's was skills. I learned exactly.
Data analysis.
Exactly.
You don't have
Yeah, I
to get
came
there.
from so like
Before we're both dead.
you can think
I don't know. I every once in a while. So,
so I chose to like focus
the only thing that I've,
because I wanted to
everything
do
seems
that
noisy.
time.
Just little tiny things that probably are just.
I think so.
Yeah, and then I think it helped too because I was coming from. I greatly enjoyed like my experience here at the academy. But also I feel I didn't prioritize it. So I didn't have a lot. So taking the 2 years to get that and then doing it. Because not only had I done like proof that I could do research before my master's, but I also
They
had
ruled out 11 things.
You guys can help me set it up. Yeah, that one. Sure. What do you need?
It's scary.
It's not a good thing. And then the blood is toxic. The blood breakdown. Which is probably what caused my seizure. When I was taking me to the hospital. So,
And then they get an airplane.
when I got there,
There's open docks that airplane ride.
it was nice to be able to have that. It only cost $20,000.
It wasn't all that much fun.
They're gonna need.
I was actually at an airplane. I remember the sunset down to the windows.
I didn't want to talk about that, actually.
No, I was able to get it.
They're like, yeah.
Yeah. They didn't view me as a threat.
Indifferent.
Yeah, that guy out there, he's getting-
Right, because I was here, I did most things.
What are you gonna do?
And then I was like, nope, never mind. Data science and ecology. But I think it all is.
Three of us on the.
Well, you could crack the whip on all those guys. Make sure that
What the current.
Fourth being biology. Pretty top notch.
We're ready to.
that's right.
We're all looking forward to Facebook.
That's great. Yeah, that's awesome. So you're leaving on the 4th?
I'll leave May 4th.
We should get together.
Who's ready?
Do you have anything else
As
planned?
like
This weekend we're going to
equatable person.
and otherwise just day things here and there.
Okay.
But major trip.
Okay.
Now they're.
Sounds like a plan.
Yeah, that's a scary.
That's what.
That's a scary.
Still we meet.
I do.
Yeah.
And I like beer too. It's completely vegetarian.
You know, I went to when we walked up to the M. It was a W when I was square, but I walked up to the M. Yeah, when I first first year, it was a W. It changed.
Yes.
When they changed it over.
It wasn't, they did, and then it looked like
It was
a
very long.
Roman numeral,
Yeah, it was
right?
very
It looked
long.
like two X's or something.
Yeah.
Yes.
For a while. So walked up to the hill above the
Yeah.
M and looked over and like, holy crap.
How big is it?
The campus or
Just the city.
the city, like the total metropolitan area is about 700,000. Yeah, the student body is about 40,000. Yeah, and then Glasgow City is like 75. They're like 750,000. The university is like 15. I got used to it. Yeah, a little bit bigger, I guess. Which
Yeah.
I gotta do, I think. But
I think.
Yeah, I did the opposite.
that's fair. Well, at some point you gotta pick one.
Well,
Yeah.
well, I went bigger, smaller, then bigger, and smaller, so I've been back and forth.
I just like. And I still do. I still do.
Oh, yeah, no, San Diego was big.
Yeah.
That was just insane. With traffic. Because I lived 13 miles from campus. I couldn't afford a parking pass at UCSD campus, so I would take a bus. But taking buses took me an hour and a half because I had to switch buses
Yeah,
to just get to campus.
yeah, that's what I did.
Some took off.
Yeah, what are you doing these?
Sometimes I rode my bike, yeah, that was a long bike
I wonder
ride.
So excited.
As far as the other trucks,
Yeah, well, here you walk all the way across town if you needed to.
Yeah.
I did.
I said in
You'll have your,
Yeah, I still have it all. It's all, I moved a lot. And so there's a couple boxes of like memorabilia and stuff that I've started storing. After I moved, I was like, this is not practical. So it's still there.
Had been. Wow. No, without that. Without that. Exactly. I thought you were going to stroke or my buddy.
Yeah, Madison, like, moving to
How back
Madison.
stuff because he missed the open.
Like when I think I hit and I hit a year in Madison. For a year.
We call that one back.
There's a bit of a house. We have a big booming tech industry that's replacing a lot of affordable housing. So it's really pinching the availability of affordable housing. We chose to do the same thing that we did here, which is purchase a random source of mine to subsidize communities. Because my stipend was well below without that addition. Most of my like cohort are also taking like small student, or they have a partner that works. There's a partner. They're taking small student loans if they have a partner. That gap.
would you do your defense, whatever that is? It was a tradition at MSU that the the defender of the student supplied the treats for the seminar. I don't know what you guys did, but we had supply our own treats.
There were no treats.
Our seminars always have treats, and the defense was supervising on your own treats. They had treats for the break. My committee told me I passed all
There you go.
Just something to keep in mind.
Yes.
Gotta
butter
them up before
Great
they.
cookies before you.
Yeah. Okay, gotta get them nice and buttered up. Yeah, yeah.
Fruit, kind of like a overgrown with two little cakes with that. If you like
Big
that
sweet guy, that sounds good.
If you like that sort of stuff.
Yeah. No, I provided a lot of beer after my class.
There was that too.
Yeah.
I don't, the last person who finished my lab, I don't think they provided the treats, and I don't think they provided the alcohol. I think those were purchased for them.
I think I had to provide the alcohol. We got a small check.
Yeah.
Maybe it wasn't even a small check. I do remember we ran out of beer. The next day I was very happy that we had run out of beer.
We got a large keg, and then I did a barbecue. But yeah, it was a good time. We did it out on Rock Creek in a campground, so everybody was camped out.
Yeah. Oh, cool.
And I still remember that night with my German friend George, because he drank a ton of beer. And he didn't want to go to bed. His wife wanted to get him to bed in the camper. I remember her leading George some fried chicken towards the camper. He was just like walking out of the chicken. Wow. Late at night.
Did you get pictures of that?
No.
Did you use it for blackmail?
Yeah.
Where is it? Where are you sitting?
I don't know. There's not much space left. Somewhere back there.
I'll sit with you.
Okay, sounds good.
Except,
Is he okay? No.
By the way, if anyone has like not presentation related questions about like how I've ended up where I am, I'm happy to talk about things. I like to talk. It makes being here. You don't have to. It's okay. Ignore me for the next. That's a fair point. You know, it's interesting that it's not on that slide. Details. Yeah, so I'm a PhD student at the University of Wisconsin-Madison. So I graduated from here in 2017. I took 2 years off. In that time, I was an undergraduate researcher, like undergraduate research assistant at the University of Utah, and then worked for biotech for 6 months. Took a much needed break and then started a master's in Glasgow in Scotland for a year, master's in the UK only a year, and then got into this program, which I work with a center funded by the CDC that focuses on vector-borne diseases. So that's generally me, which Morrow or Gilbert also. I feel like there's already an audience and I haven't been interested. I'm not allowed to talk yet, so like I don't. Feels a little strange, but really good question. So a couple of reasons. First, the application cycle is very different for the UK. So in the US, to get into a master's, right? Like let's say if you want to start this coming fall, you already have had to submit your application like last fall, and then be doing interviews and committing right now. In the UK, they have rolling admissions up to about 2 months before the master's. So I decided in May that that's the program I wanted to get into, and I was able to apply in May and start in September. So that was really cool. The other thing about the UK is most masters in the UK are 1 year instead of 2 or 2.5, which that was already coming on my 3rd year out of undergrad. I kind of was ready to get the ball moving. I didn't want to stay for too long. And then UK-based masters are either MRs, which are Masters of Research, where you do a 9-month research project, or they're MSs, Masters of Science, where you do 9 months of coursework and a 4-month research project. And so because I knew I wanted to do a PhD, doing a Master's of Science, where I developed a lot of skills that I could then apply later, was really appealing, as opposed to having to spend 2.5 years on a research project that like maybe wouldn't be directly related to what I would do next. I also think that living abroad is a really cool experience, and if you can find a way to do that and afford it, and or pay for it through education, it's really cool. Thank you for asking a question.
Katie, what was your favorite part of going to school here?
The small class sizes. I think that was really important, actually. I think that like having now been to like large universities, the University of Wisconsin is 40,000. So lower level courses can have hundreds and hundreds of people in them. And it's really hard for professors or faculty to care if there's 600 of you in class. And so I think that one-on-one interaction that you get here, like, spurred me to keep thinking about academics and about research as like something that was actually relatable to me and not just like check a box, get a class done, finish. I felt like people cared, and that's, I think, was big for me.
We should start.
We can?
Wait.
I don't know how this usually flows. Do you have people coming in or not?
I don't think much. Generally here right now. So.
That's fine with me. I'm fine with you.
Sure that.
I can do that.
These are my Yes.
Yeah. You're gonna see my name on the application.
Okay, all right. So, we're gonna wait. Apparently, environmental sciences straggles in at 4, and then they don't put it up. YouTube link. So, actually watch it.
Oh, great.
Well, a lot of faculty watch it if they can. Yeah, and actually our new, so we got a Carl colleges, but our new just here this year. So hopefully, I don't know if he'll let me get his dad.
Yeah,
You guys get it up. And he did his PhD in New Zealand.
Oh, very cool.
Yeah. It was a virus in possums that actually killed cattle.
My brain knows what that is, and it's just too far there.
Yeah. But I think he wants to start doing some CWD. Yeah.
Yeah, and then.
And then that was
I still got the dog that I got. Yeah, I don't know what dog now.
I got a dog. I got a puppy my first year of grad school.
All day I felt like that.
He was actually on his dissertation because there were times when he just gets so pissed off on his kid. Cause the stress to outweigh. But I just got it. And then since we can't be here, I got he finally passed away. And so we adopted a couple of dogs from the shelter since then. And they passed away. So this year in December, we adopted another dog from the shelter with the second adopted puppy. And I have 25 years. And I forgot all the craziness of puppies. It's crazy. You want to walk out overhead, just chasing waves. It was all chasing. Got it in the truck and off the garage door to let him out of the garage. So we got out of the garage. And I don't know if you've seen Christmas Vacation. Seen Squirrel in the house. That's what happened when we were around.
You guys can sign up for your meeting tonight. I didn't sign up. Like, I'm not like in the class. She's like, go in. Yeah, I'm wrong, but sign up. So I did. She's like, why? You're in the class. I like this. That's 50. Is it worth it? I mean, it's actually worth it. That's what I have 50. Yeah, 52 actually. On the more accurate one.
So let me know.
No,
Quiet folks did, we'll get the show through. And then you still have our pop teas afterwards. You're still working on that. Okay.
Oh, it was funny. We went to like an exec to him, right? And I was like, I think I remember how to get there. I think I remember how to drive up to there. For a while, I'm breaking that road every day for like 3 years. So like, it's been a while. Yeah. I had this slight sense of nervousness when I was like driving down. I know I could drive, like, gosh, me having time. But it's been like 4 or 5 years. But I had a moment of like,
Remember Whitehall?
yeah, I was like, I'm going to be.
he's gonna go just outside us.
Well, that's good. But when did you find out?
That was like 11 years ago. Yeah, I was supposed to see my aunt and uncle last night, but I actually told them. I talked about it before the date change, so I had to go there right before the date. Not last night, and I never understood that. So they were not expecting us. And we drive up to the house, it's dark. I'm like, wow, they have so much confidence in me. I know where I'm going. As we go with that, so we go in the house, we're walking up to like the loft upstairs, we're gonna stay, and all of a sudden it's like dogs sound off from the loft. I'm like, oh. So like I can go back downstairs and I like pull out my phone, like text my aunt, and I look at the text, and the text right center.
Were they there or not? They were either asleep.
Yeah, they were asleep, or whoever was there didn't feel the need to get out of bed and figure out why the dog was barking. I was honestly okay with that. So yeah, I sent her a text this morning, and I was like, so funny story.
Yeah, so I was.
So how much fun is counting the things?
So we're like rapidly trying
And so are you're presenting, this is stuff in addition to what was published?
Yeah, so I have a couple of stuff that I
Okay, so that's what I thought.
yeah, yeah.
That some of it was published.
Kind of eerie. No, I didn't. So because I have more I confirmed what I said so, and I have some more things here.
And I made.
There's also
Oh, yes.
yeah, I do get to take it with my PI.
Okay,
She enjoyed getting to stick with me.
nice.
Yeah, I'm so, I was on an RA this year, this year I'm on the center was refunded, but it wasn't refunded.
Well, yeah,
But
it's good practice.
yeah, exactly. Yeah, and I was lucky, university.
Well, I told you my PhD advisor's PhD is at Texas. Or at least it was when you started. It's just a song.
Everybody's like, oh, where do you want to go?
It's like, do like a.
Did you go big? Did you walk all the way to Lewis and Clark? Thank you. Did you get my text?
I did.
Oh, okay. And we walked in and I was like, oh, where's the park?
My dad actually plugged into Hey, Pops, do you remember when you did On the Rocks here? What year that was? Was that 2016?
You're good.
2015 and 2016. Yeah, and he's a little bit.
Yeah. Those were small symptoms. There's only 9. So, and most of them come to these anyway. They're part of the biology club. And they're the ones that bring in refreshments. You know, when you're an undergraduate, free food, and there's the fees are still carriers. Just permanent. Chemistry. Because they can have so much money in private industry or other schools. Get in quick and fortunately, is what it's been. I have some kids that want to be here. We were able to rotate. Okay, folks. I think we're gonna go ahead and get started here. It is a real pleasure for me to introduce today's speaker, Katie Suson, as she is a Western alumna. She received her Bachelor's of Science in Biology here with what was it? Molecular bioscience option is what she got in 2017. And then she received her master's in quantitative methods in biodiversity conservation and epidemiology.
Yes, that is all on the degree. Like on the sheet of paper, all of that is there. That wasn't a description, that is the title.
And that was from the University of Glasgow in 2020. And that's Glasgow in Scotland, not Montana. They don't have a college in Glasgow, Montana. And she is currently working on her PhD in comparative biomedical sciences at the Midwest Center of Excellence in Vector-Borne Disease at the University of Wisconsin at Madison. And today she'll be telling us about some of her research on the Asian tiger mosquito, Aedes albopictus. Some of this work was fairly recently published in Environmental Entomology and was subsequently featured in Entomology Today. But she has some extension to that work that she will be adding on today. So without further ado, take it away, Katie.
Great, thank you. I think some of you may have caught that interaction, but if you didn't, this is actually really cool for me because way back when I was here in 2015 or 2016, my dad actually presented for the On the Rocks geology seminar in this room. So it was an interesting experience to now be here instead of there. I hope I do as well here as I did there. So bear with me a little bit. So as Gilbert mentioned, I am at the University of Wisconsin-Madison. It's really fun having been at like UMW and UWM. Those are not. And I study effectively disease ecology. So I'm interested in how ecological systems create disease. And for that, I'm going to be specifically focusing on a type of mosquito because vector-borne diseases are a global problem. There are currently 17% of all diseases are caused by vectors globally. Of these vector-causing species, our transmitters are arthropods. We have things like ticks, we have kissing bugs, we have flies, but most importantly, mosquitoes. Mosquitoes make a huge chunk of these transmitted diseases. And consequently, understanding the ecology, how these mosquitoes, which carry and transmit disease, interact with us and with their environment is really important. So when we think about specifically mosquito-borne disease, which is what I'm going to talk about today, I acknowledge that I said there's lots of them. We're going to talk about mosquitoes. So almost 700 million people contract a mosquito-borne disease every year. These include things you may have heard of: malaria, dengue, yellow fever. They may be some ones you're less familiar with, like Japanese encephalitis or like Eastern equine encephalitis. I don't know if we get triple E out here, but it's a big problem in the Midwest for horses too. We also have things like West Nile and Zika. West Nile is another big problem in the Midwest. These diseases are transmitted by a variety of species. Some of the most significant ones are Culex species mosquitoes and Aedes species mosquitoes, and also Anopheles, which is the most important mosquito for the transmission of malaria. Malaria is a killer of 1 million people plus a year. And this is already concerning, right? In a in an unchanging system. That's important, right? But we aren't living in an unchanging system. We're living in a system of climate change, and mosquitoes are arthropods, which means they are dramatically impacted by climate, particularly temperature. If you have not seen one of these before, this is an anomaly graph. So what it's showing you is from our standard, which is 1980 to 2020, how different was 2015 to 2021. So the redder it is, the warmer it's been in that time frame. The bluer it is, the colder. And it's important to note that like nowhere is blue, right? Nowhere is really getting colder when we look at anomalies. Everywhere is getting warmer. And this exists everywhere, but this is, we're going to focus for a moment on sub-Saharan and Central and Southern Africa, because that is where malaria is a really high burden. Climate change changes risk. It changes and shifts where these risks exist. So with these shifting temperatures, precipitation, and climate stability, we have changes in who is exposed and who has risk of a disease. This is some really cool work that was done to try to predict where the greatest burden of malaria is. And what we can see is as we go forward in time, the burden of malaria actually changes. It shifts and it moves. Why does this matter? Because right now, the majority of spending to try to prevent malaria is done here. But in 50, ooh, you said it was touchy, you weren't joking. The majority of spending is done here. But in 50 years, that's no longer the area of main risk. So if we know this now, we can start planning with policy, with education, with outreach for this kind of inevitable future shift. I'm specifically talking about anopheles and malaria here, but this doesn't just apply in tropical regions. This also applies in temperate regions. Again, it's that same figure. This isn't staying the same or getting colder either. It's also getting warmer. And what that means is the mosquitoes that we have, things like Aedes species mosquitoes and Culex species mosquitoes, which can transmit more diseases than Anopheles mosquitoes, are being exposed to changing climate. And that changing climate changes risk. We are going to leave the Culex species mosquito. It's a very interesting mosquito, but it is a native mosquito which has its own set of problems, and instead we're going to focus on Aedes. Aedes species mosquitoes are most significant for their transmission of dengue, yellow fever, chikungunya, and Zika. I don't know with like the younger people in here, sorry, if y'all remember that in 2016, if you were aware that in 2016, there were some pretty significant Zika outbreaks emerging in the US, particularly in the southern United States. So we became very worried about where Zika would exist in the US. And that's kind of the origin of when my work started to become relevant. So Aedes albopictus is what we're going to worry about in this region. So we talked about Aedes species. We're going to focus on one of them, Aedes albopictus, or the Asian tiger mosquito. The Asian tiger mosquito is a really interesting mosquito. It has both a tropical and a temperate strain. So that tropical strain that exists in warm places, year-round it lays normal, favorable condition, happy eggs that hatch easily when exposed to warm temperatures and water. For temperate mosquitoes, they don't always lay these nice, happy, easy hatching eggs. They also lay something called diapausing eggs. If you want to think of diapause like a hibernation or a homeostasis for an egg, that's a reasonable way to think about it. Effectively, these eggs are in like a temporary suspension where they are temperature resistant, desiccant resistant, and are able to survive harsh temperature, like harsh climates that they wouldn't be able to survive in this rapid release stage. The fact that this exists, the fact that this mosquito does this, I thought I moved it for a second, is important because in cold regions like here, like Wisconsin, like most of the northern United States, that winter stage, that diapausing only eggs, that's their linchpin, right? If this doesn't work, if they can't survive this time period, the life cycle falls apart. And they only survive as eggs during this time period. That's the only part of the ecosystem or part of the life cycle we have to worry about in winter, is can those eggs survive? So from a prediction, from a modeling, from an understanding ecology perspective, winter is really important. So that's a little bit about Aedes albopictus biology. And if you hadn't noticed the way I was talking about it, temperate and tropical, that sounds like a mosquito that can exist a lot of places. And it does. It originates in Southeast Asia, East and Southeast Asia. But since the 1970s has spread rapidly to every continent except Antarctica. So we have populations now throughout the world, including in the United States. This spread is concerning, right? They now have to worry about more places with risk. Additionally, Aedes albopictus is a highly aggressive mosquito. So diurnal meaning daytime, it will bite it likes to bite people, it likes to bite them during the day. So even if these mosquitoes aren't actively transmitting a disease, they are a nuisance. They have massive implications for quality of life, particularly when they're in high densities. Finally, as I have mentioned a couple times, this mosquito can transmit disease. We have already 3 instances of Zika or chikungunya transmission, an outbreak that was attributed solely to Aedes albopictus. So we know that the invasion of this mosquito to new areas has led to outbreaks of disease. So I have now kind of outlined what albopictus is, why we're potentially worried about it. I also want to focus now on the US and where it's been in the US, because my work is focused inside the US for now. So in the United States, the expansion began in the 1970s. That expansion began in Texas and Florida, and then has moved northward. In 2017, people on my team and in my lab identified and I detected Albopictus in Wisconsin. So we know it's gotten all the way north to Wisconsin. It should be noted this map is slightly out of date. This map is from 2015 technically, so we're missing some key spots. So what are the factors that are defining its expansion in the United States? I already mentioned, I haven't necessarily specifically mentioned it, but summer habitat matters, right? The time when all of the life stages are present is going to impact where they can survive. More importantly, we have overwintering survival, that a time period where they can only survive as an egg. And we have dispersal. How do they get where they're going? They're mosquitoes. They're not flying thousands of miles by themselves. I guarantee you, they have help. And so both this overwintering survival and this dispersal can actually be associated with trade and with tires, which is kind of a weird left field thing to add into this conversation, but tires matter. Aedes albopictus is a container breeding mosquito. It means that it uses small spaces to lay those eggs, which means that those small spaces are acting as something called a microhabitat. Microhabitats are critical for protecting species from harsher, large-scale conditions. Audience interaction moment. You'll have to deal with this. So everyone, just stick your hands out. Try not to hit anyone. Please humor me. Thank you. This is roughly a 2-meter space. We literally just had some kind of bug fly, which I found very appropriate. This is a 2-meter space, right? 2 meters. That is how we measure most environmental spaces. I want you to think about a mosquito. It doesn't occupy 2 meters, right? It occupies a space this large. Its entire habitat isn't necessarily 2 meters. So what's happening inside the space a mosquito occupies can be extremely different than that 2-meter space that we measure things in. And that's important for oviposition. It's important for dispersal. It is what a lot of my work focuses on. I wanted to reiterate that we are seeing changing risk with Albopictus too. These were some large-scale predictions that were done. So this is looking at those big temperatures, not at little temperatures, big temperatures. And we do see that we're seeing this shifting risk as we move forward. If people aren't familiar with these notations, these are climate change predictions moving forward. So these are the most extreme climate change prediction in 2050 and in 2080. So we are expecting to see these shifts in risk, but I argue that these shifts in risks are likely underestimated or underapproximated because these type of calculations only account for those 2-meter spaces, not for the little spaces. So my overarching objective of my work is to apply field and laboratory studies to define the effect of habitat use on experienced environmental conditions of Aedes albopictus to improve the prediction of Albopictus expansion in the United States. So overarching, what I'm trying to do is in the future, is to predict where mosquitoes will be in the future with higher accuracy by accounting for small spaces. So the first thing I did for that was a series of work that was done in 2018 and 2019. If you're really paying attention to the introduction, you notice I started in 2020. So this data already existed when I started. But I have a background in computation and in data analysis, so I was brought on very specifically to continue to work with this data. So the objectives of this set of data were, one, to determine if tires were actually creating a suitable microhabitat. We knew they were associated with dispersal. We knew we were seeing emergence and establishment near tires. Were tires actually making it easier for Albopictus to overwinter? And second, could snow cover? Because I live in the Midwest, which is very snowy, kind of like here, and snow is actually insulative, which sometimes still hurts my brain because it is cold, but it is warmer than the air. Does this have consequences on the insulation of those microhabitats? So to do this, we first need mosquitoes. And I want to talk a little bit about how you get mosquitoes for a lab study. Because if you have never been exposed to this or seen it, it is kind of absurd. So you have to generate cages of mosquitoes to generate things like eggs for studies. So to do that, you work in an insectary. Insectaries are warm, humid, and have a lot of sunlight, or light to approximate sunlight. In that space, you hatch eggs. Eggs are hatched from papers that look like this. So each one of those little dots is a mosquito egg. They form these small instar larvae in the water, and then you have to count those out, which is a laborious process that involves glass-tipped pipettes and a lot of light to pan out about 300 per pan. If you put more than that, they don't grow very well because mosquitoes are weirdly temperamental in labs for how prolific they are in reality. This is our amazing lab manager, Kathy, who tells me that I can't count to 300, so she will do it for me. From that point in the pans, they are fed. They are fed, if you're curious, twice ground fish food. So like fish flakes, if you ever had a pet fish, mosquitoes like those too. So they get them in smaller particles as they go through 4 stages of larval development. After that, they are pupae, which are these weird looking shrimp things. The pupae are then pulled from those pans, placed in these small cups, and then moved into a cage. In that cage, they're allowed to become adults, and they are fed on 10% sucrose. Fun mosquito fact, only female mosquitoes bite and draw blood, and they only take blood when they are preparing to lay eggs. So the rest of the time, they are living off of nectar because they are pollinators, which is a weird thought. And the male mosquitoes never take any blood. They are just living off of sucrose or nectar for their entire lifespan. So for those females to lay eggs, which we need to maintain a colony or do a study, we have blood feeders. These blood feeders are filled with sheep's blood and covered with like a parafoam membrane on which the mosquitoes can perforate. They're also put on a heater because mosquitoes are mini vampires and need body temperature blood. From that point, you now put egg papers in, you regenerate those egg sheets we saw at the beginning, and the process starts all over again. If you recall my conversation on Albopictus biology, you'll remember that they lay 2 types of eggs. They lay non-diaposing eggs, and they lay the diaposing eggs, which are important for overwintering survival and how they are surviving in cold winters. So we need to generate those, not these, because these are normal eggs that would crumple at cold temperatures, and that's not what we want to study. So to generate diapause eggs, we start the initial steps, the generation of egg paper, hatching eggs, and counting them in our nice, warm, happy space. And we move them then into a less warm, less happy space. Still pretty warm, 27 C, 80% relative humidity, but extremely importantly, it is comparatively dark. Photoperiod, the amount of daylight, is the key trigger for these mosquitoes to lay diaposing eggs. If you think about that from like a seasonal or ecology perspective, that makes a lot of sense, right? As the days get shorter, they're more likely to lay these cold, hardy eggs, which makes sense with seasonal changes. So once we've generated specifically those diaposing eggs, we terminate this cycle of mosquito maintenance, and we instead transfer these sheets we cut these sheets into even sections, photograph them, and then count the number of eggs per section. It is as laborious as it sounds. These eggs are very small and must be looked at under a microscope, so lots of time is spent counting them. They are then stored in bags, and they are deployed into our field study. So what does a field study look like? The 2018-2019 field study took place at 15 sites across 5 locations in southern Wisconsin and northern Illinois. These sites were a combination of homes and industrial sites owned by mosquito abatement districts in the area. At these sites, in each tire, so we had 1 tire, we had 2 egg sheets, which were contained in these whirl bags. We had an eye button, which is a form of temperature monitor, so it's taking the temperature inside the tire. And we had an additional eye button monitored, again, so touchy, on the stake to monitor external temperature. I said we were interested in snow cover, but that was something that we could only account for with SNODAS, which is a data assimilation system that takes actual snow measurements and weather reports across the United States and then approximates those into a daily snow depth. So it's able basically to extract a daily snow cover for every square kilometer of the U.S. every day during the study. This year was an interesting year to do this field study because it was cold, like really cold. We had a polar vortex that year, and we had temperatures down into the -30s at almost all of our sites. This is a really good opportunity because we are interested in how hardy this mosquito is at surviving in these really cold winters. So from that, we were able to then hatch our mosquitoes when they came in, hatch those eggs out of the field. They were in the field for about 5 months. After hatching them, we were able to look at relative survival. We calculated relative survival because we had eggs in control in the lab. And we knew that not all of our eggs would hatch all the time. They just aren't always that viable. So by comparing our control to the eggs in the field, the sheets in the field, we have some idea of how harsh the conditions were. What we found is that our southern sites, should be noted that both in Champaign-Urbana and in Kankakee, there are established populations of Aedes albopictus. We find Albopictus every year surveilling down this far south. There was no survival, but north, so in Wisconsin and northern Illinois, we saw survival, abated small survival, but we saw some amount of relative survival. So the question becomes why? Why at our northern sites, which were colder, did we see survival? And at our southern sites, which were warmer, did we not? The answer comes down to something that I alluded to before, which is snow, or changes in temperature, I should say. So if we look here, this is New Berlin and North Mosquito Basement District. These are those two sites with survival. We can see that this gray line, which is a temperature outside, was substantially colder than the dashed line, the temperature inside the tire. But this was not true at all sites. This only applied at these sites with survival. So the question is, what's different about these sites comparative to the sites further south? The answer, which I've alluded to a couple times, is snow. So if we look at these two sites, this red and this kind of strange greenish color, those are the two sites with survival. And the amount of snow they had, particularly during this crucial period of diapause, is higher. This is also, this period right here, about this 2-week period, was the coldest period of the year. So during that coldest time of that year, we had more snow at the sites with survival. Now, looking at a graph is great, but I am actually a computational ecologist, so I like numbers. So I use something called a linear regression or a mixed effect model, which I think in this case is a mixed effect model, to look statistically at what the consequence of snow was on the temperature inside the eggs. This is called a forest plot, and it may not be something you're used to, but basically it's a way of representing what's happening in this equation. This equation is relating the outside temperature to the inside temperature and accounting for the amount of snow. And what this is showing us is that as we increase our snow depth, we increase our internal temperature. So this line, this 0 line, anything over it means that our temperature inside the tire is substantially warmer. So we have some basic insulation just from it, so touchy, just from it being a tire. But we see that adding snow over about 100 millimeters or 10 centimeters increases the insulation on that tire. So tires are warmer with snow on them. Does this have an impact on survival, though? I kind of have said it does, but what does that look like? We represent it graphically. So to orient to this very busy graph, we have external temperature down here, internal, so that's the tire temperature. So the tire is getting warmer this way. The external temperature is getting warmer this way. Our snow depth, the bluer it gets, the more snow we have, and these triangles are where there's survival. We have two distinct, so again, increasing temperature this way. We have two distinct clusters. We have one cluster up here, which has survival, and one cluster down here, which does not. From that, we can see that deeper snow and warmer tire temperatures up here have survival, whereas less snow and lower tire temperatures are not seeing survival in this year, right? This is a single year study, so don't get too excited. So let's take that into consideration. What does that mean in the context of the Midwest? Like, okay, great, tires are warmer. Great. What does that mean? That means that if we think about climate-related survival, if we think about the tolerance of this mosquito, if we don't consider microhabitats, their tolerance likely exists somewhere in this band. This band is right around 0 degrees C. So somewhere in this range, to orient, there's Wisconsin, Illinois. Somewhere in this range, these mosquitoes should be unable to survive past. If we incorporate microhabitat-mediated survival, so we add that insulation factor that we get from tires, that survival goes up quite a bit. So now all of a sudden, somewhere in this band, which is much higher, we're seeing survival. It should be noted that I'm looking at past values here and future values here for temperature. So we're accounting for climate change in this kind of quick and dirty approximation of what the impacts of this are. This is major implications for management. Microhabitats can be used to explain unexpected adult populations, either in abundance or distribution. Identifying these sources of microhabitat can be critical for targeting surveillance and control, and it reinforces the need for targeting controls, right? If we have these emergencies or these existences highly tethered to these microhabitat spaces, we need to be making sure that the types of controls we use impact or infiltrate these spaces. This is the work that was mentioned that was published. It also had a popular press article, which was a first for my lab. So this is my pat on the back for me. Just a moment of yay, Katie. Okay, which this was really cool. This was a really interesting thing to find, but it is a single year of data. And ecology is about patterns. So instead of keeping it with this single year, I wanted to see if we could see this again. What does it look like if I look at 2021, 2022? So we're going to roughly repeat this study, but we're going to focus on a couple things. We're going to work harder to define that microhabitat used by Aedes albopictus, right? We did some rough approximations on it. We did some statistical analysis. Let's see if we can make that even better. We're also going to expand the geographic extent, right? We looked at only southern Wisconsin and northern Illinois. Let's make it a little bigger. Let's see if we make it colder, a little bit warmer, if this trend holds out. And finally, we use this really kind of powerful tool of this data assimilation for snow, but I have no proof that the number that this spits out for me is representative of what's happening on a tire. So let's make sure we can check that that approximation I'm using actually works in my system. So for this study, we expanded geographically. If we recall, last time we were in about this much area. We have now pushed out to all of Wisconsin and Illinois, so about double the geographic extent. These field sites are co-located with weather monitoring stations run by the University of Wisconsin-Madison, Michigan State University, and the University of Illinois. I acknowledge none of them are in Michigan, but Wisconsin doesn't want to run their own extension sites. So with those, I was able to have sites that looked a little bit like this. So I have weather monitoring, which is high resolution, large input data, right? These are established weather monitoring for my external data. I then also have my site. So here I have, instead of one tire, I have 12 tires, so 2 at each location. I have the weather monitoring, this external system. I have SnowDAP, which I'll extract later from the data assimilation system. I have these 2 cameras on this green stake, which are used to verify the amount of snow depth that I'm seeing daily. And I have my 2 tires, which contain 3 8 sheets per tire, and this hobo temperature monitor that is letting me know what the temperature is in that space. I apologize for all the extra lines on this graph. Hot tip, don't use PDFs in PowerPoint. Use TIFFs or JPEGs. So what we are seeing here is a comparison of that SnowDAS data versus that on-site measurement. Right? So I had that game camera that took a photo every day. I generated a photo that had a snow stake on it that I effectively had to line the snow up to the snow stake using an image processing system. Then it spat out how much snow I had on the ground. I compared that to the SnowDAS, that is approximated system. And what I see is, so SnowDAS is this dark line, and the on-site is this light line. And what we can see is that they trend roughly the same. SnowDAS struggles a little bit at higher snow volumes, but roughly speaking, when there's a peak in real life, there's some kind of peak in SnowDAS. So it's not perfect, but I'm at least seeing the correct trend, which may be all that matters for the prediction work I'm trying to do. So that was really encouraging. We can look at this another way. So if we had perfect one-to-one, my SnowDAS measurement, my on-site measurement were perfect, we would follow this dashed line right here. Unfortunately, reality is not perfect. So we instead have this darker dashed line right here, where we can see again at those high volumes of snow that so sensitive. At those high volumes of snow, we're falling off a little bit. We can't quite predict as well, but we again are still seeing at least a following of the trend. Okay, so what does SnowDAP look like for that year? Great, I said that they trended well. What did it actually look like? So we had kind of what we'd expect as we go further south. Our snow depth goes down with a strange exception in Carbondale for a little bit. But overall, high snow up north, less snow down south. Okay, what did that do for my insulation? For my insulation, okay, I acknowledge the color gradient on these points may not be quite as clear as I want it to be. Again, TIFFs, JPEGs, not PDFs. Darker colors indicate less snow. As the colors get lighter, you have more snow. Any point above this dashed line would mean that it is insulative. So we can see generally that snow creates insulation, right? We do see some, again, of these dark points, so less snow points kind of falling off. We're also looking at those those are kind of external temperatures and internal temperature driving this equation or this graph. But yeah, we can see that very few points are falling below that, and most of those points are dark, meaning not a lot of snow. Which is, again, what we saw in the last study. But one thing we can look at in this set of like this year that we couldn't look at the year before is how the tire was covered. Was the tire completely uncovered, aka no snow? Was it only covered only on the side, only on the top, or both covered? Or was there too much snow covering the camera lens? So I have no idea what the tire looked like on that particular day. There's gonna be a few of those. But what we can see is that, which makes sense, as our snow increases, more and more of the tire is covered both on the side and on the top. That's really logical. It's good to see that that works out in reality. What does this amount of coverage have to do with insulation? We can see, we have another one of these forest plots. Remember, further away from zero, larger effect. If the bar overlaps zero, not a significant effect. So what we can see is that when we only have the top covered, the tire is roughly the same temperature. This is probably because we aren't really getting insulation. Maybe it's cutting out some solar radiation from the sun, so we're just not getting that warmth. But once we start, and that's why you should notice that it's actually colder than the uncovered tire. I think that's that loss of solar radiation. You put a little bit of snow on top. The black tire isn't being warmed anymore, so it's a little bit colder. And again, sides only covered, you're maybe not getting insulation, so we don't quite see a significant difference from the uncovered tire. But when we cover both the top and the side of the tire, it is warmer by a bit. So now we know we have a rough metric of, if we look back at this, right? Side and top covered, we only start seeing that a ton up maybe at 300 to 400 millimeters of snow. So we know that we need quite a bit of snow to cover it completely, but we are still seeing insulation at those lower values. Okay, excellent. So now we're going to do some computational stuff. We got this. Fitting regressions is a great way to look at the significance or predict a trend for the internal tire temperature compared to the external tire temperature and environmental conditions. So to do this, I want to make sure that I'm fitting a best form of this. It is the best, most validated and best at predicting. So it can is most useful for extrapolating new data for sites and years I don't have. So to do that, I use my two forms of data separately to develop independent regressions. So not considering the other set of data. I then compare those. And what I find when I do a comparison is that I get this equation. This equation is going to look similar but slightly different to the equation that I showed you for the 2018-2019 study. It still has the external temperature impacting it. It still has the snow, but it has one additional thing. I knew that was going to do that. It has this term right here. This term is an interaction. So it's telling, what it's saying is that snow cover can interact directly with the ambient temperature, which then impacts how much insulation we have. I don't know, you won't see a forest plot for this right away because of this interaction, you have multiplication, which means you have negative numbers to make positive numbers, which makes forest graphs look weird. But trust me, it works. It is warmer with more snow, and it is warmer when the external temperature is warmer. So I now have a regression that fits best. So this is my best fitting regression. With that, I need to validate those. To validate those, I will do a combined set of data. So I will take these two data and pool them. I will split them into a testing and a development data. With that development data, I will reproduce these best regressions. So I have a best regression from the 2021 data. That's what I originally made it with. I have one from the 2018-2019 data, and I have it from this development data, which is a pooled combination of these data. What I can see, PDFs, man. What I can see is that these three regressions are really reproducible. Regardless of what data source I'm looking at, I'm seeing a similar trend. This is when I said these forest plots look kind of weird. So I know that in the last two times I showed you a forest plot, I told you that if it was below zero, it would be decreasing the temperature. We are now dealing with interactions. So they are multiplying together to make positives. I almost tripped. So what we are seeing is, although we have kind of this trickling negative, we are seeing more snow, more interaction, warmer temperatures. So we're again confirming what we saw. This isn't new now. We've confirmed this again. Finally, we have to test with our reserve data. We have to make sure that with data that has never seen this equation before, that it can predict it correctly. And luckily it can. So what happens when you run these predictive data is you display a graph without dots. When you run this predictive data, we see this really kind of beautiful ticking where as we get darker, we're getting more and more snow. So 1-to-1 would be effectively no insulation. The tire and the outside temperature are the exact same. Again, we're looking at daily internal and external temperatures. As we add snow, we see this tick of it basically flattening, meaning that we have more and more insulation with more and more snow. And our prediction works really, really well for this. It tracks beautifully. So I can successfully predict the temperature inside a tire. Round of applause, please. No. That's actually really cool, but I acknowledge that is a weird thing to be very excited about. If you may have noticed that I have not talked at all about the survival of the eggs that were inside that second round of tires. There's a reason for that. And the reason is biology/ecology is obnoxious. So things don't always work out perfectly. The survival in these tires did not follow a trend that I was expecting. What I was really hoping to see was that I had survival at southern sites. Somewhere in the middle, I lost survival because it was too cold, but there wasn't enough snow. And then somewhere up north, I recovered survival because my snow was insulative enough that it saved my eggs. That did not happen. There's a couple reasons it didn't happen. One, it was a low snow year. That's a big factor. Although it looked like big numbers, but the largest number of snow for that year was substantially lower. So I didn't have large amounts of snow. I also had a really cold year. So I picked these sites to follow a January mean temperature starting at 0 to about -9, which is well past the survival of Aedes albopictus. The actual January mean temperatures for this year were this right about here was -11. So it was cold. But right here, which is where we end survival, was about -7. So it looks weird because I was really hoping to see this kind of beautiful like emergence and then disappearance of survival, but it's actually following what I expected to see given the temperatures that were actually experienced there. I can see this too when I look at these analyses. This is a lot of graphs with dots and lines, but the main thing to take away here is we're looking at these significance values. So for these 3 right here, we saw that conditions experienced inside the tire correlated with survival of mosquitoes and mosquito eggs in the tire. I haven't mentioned, I didn't even touch it. I haven't mentioned growing degree days, but growing degree days are a really common metric in pest and agricultural management. It's a way to think about how much thermal energy is in a day and how that results to arthropod development. So mosquito or insect growing. So what we're seeing here is that you have more growing degree days inside a tire and your eggs are more likely to survive. Makes sense. Warmer means survival. Excellent. We're also seeing that the fewer days you have below -12 is a lethal cutoff for Albopictus eggs usually. The less days you have with at least 1 hour below that temperature, the higher your survival. Checks out. And this one here is just that January mean temperature, so warmer Januaries, better survival. All checks out. This is a little interesting. We had wondered if fluctuating temperatures, if lots of changes inside that tire, which would maybe be indicative of a less insulated tire, we wondered if that would have an impact on survival. And the answer is it doesn't. It's not significant. We don't see a trend with the amount of fluctuation in a tire impacting survival, just with the overall larger scale warmth of the tire. Cool. So to sum up that second study and what it means, first off, that we have microhabitats, again, we've confirmed they can explain unexplained adult populations, either in abundance or distribution, so we can double check that, still makes sense. We saw that the environments inside key microhabitats can be accurately predicted, and this is huge, and I'll talk about why. I'm going to talk about where this is going next, why this is so important. And then because of this, we can now improve future distributions of Aedes albopictus. And I kind of keep talking about that abstract idea of predicting or defining where Albopictus or where an invasive mosquito may exist. Why do I keep talking about it? Surely someone has done that, right? Like that sounds like a really logical thing to do. And people have done it. People have been trying to do it for a really long time. So defining and predicting the limit of Aedes albopictus expansion is a really important tool. It absolutely is. And so how are we doing that? And is that done well? So we're going to talk briefly about a couple ways that's been done in the past. The initial way this was done was something called early or pattern-based methods. These pattern-based methods basically looked at conditions in the native range and applied those conditions directly to an invasive range. So for Aedes albopictus, it's native in East Asia. So the temperate Albopictus were where they were correctly surveilled mostly in Korea and Japan. The conditions were recorded. And then those conditions were just directly applied to the United States. So, okay, if it survived at -3 or -1 or -4, it probably can survive at those same temperatures in the US. So we'll draw a line that matches that same large scale survival, and we'll have a prediction. So this work was done in 1987. And although not wrong, it is incomplete, right? This is a very broad scoping line that just kind of draws a line across the country and says, close enough. This is where it's going to be. We have gotten better at this, particularly with computing power. So with better computing power, we can now use things called correlative methods. Correlative methods now use a combination of presence and absence or presence and background points of mosquitoes. So these are things collected through surveillance efforts. And macro habitat variables found in the environment. Again, think those like 2 meter or bigger variables to create amalgam, or those are then applied into a modeling algorithm. That type of algorithm, there's lots of them. There's some that are machine learning based. There's some that are this more kind of statistical based, like I've been showing you earlier. And again, that's a really important step that I skipped, is you have to both subset these into training and validation data. So can you prove that it works? You apply it to this algorithm, you then use the extra data to validate, and you can then say, okay, here's my future prediction. Given the next set of conditions, here's what it's going to look like. So that can look something like this, where we have our yellow boxes are where we've seen Albopictus, and the lighter red is the amount of likelihood that you're going to see Albopictus in this space. This seems like it makes sense, right? If it was there in those kind of conditions, it might be somewhere else with the same kind of conditions. And it works, sort of. There are some limitations to this. So we have these unexplained emergences, right? This prediction versus reality. Unexplained emergences. We have them in Minnesota. We have them in Nebraska, Colorado. We also have them now in several places in Wisconsin. So we aren't quite capturing what's actually happening on the ground. So questions are why? I've given you one answer. Those microhabitat small spaces. There is a second answer. Climate change is hard. Correlative techniques require you to assume that your ecosystem is existing in equilibrium, that it works this way and it will always work this way. Climate change is not super conducive to works this way, will always be this way. So we have to figure out ways to both account for climate change and to incorporate smaller scales or specific ecological variables that could impact that survival. So that this nice and simple figure that of like, we just do these things, all of a sudden really quickly starts to look like this. Start having to add steps. I am sorry, everyone, okay. So a lot of these steps look the same, right? We still have microhabitat variables. We still have mosquito presence points. We still are subsetting those into training and validation. We are still using that same type of algorithm. So what are we adding? We're doing a couple of things. One, we can think more specifically about winter and summer conditions. This is obviously ecosystem dependent and species dependent. We can think more specifically about conditions. And particularly for winter, which we've decided for Aedes albopictus is a linchpin, is an important part. We can also work harder to create these micro and macro habitat correlations, particularly for thermal events, so for that temperature. Using this is kind of a placeholder equation. If you remember that larger equation that I kept showing and telling you was important, that's that equation. That equation allows me to take large variables that we can collect for huge geographic ranges and turn them into small variables you could never collect at scale. With those understandings, we now have a microhabitat set of variables. We can understand what's happening in a small space and apply that into that modeling algorithm. We can then use the same method to, I should note this one too, this is important. We also need to decide where microhabitats exist, right? I just said that I can tell you what's in a microhabitat, but where does it exist? So we can use things like urban spaces or proximity to a tire center or to roads, these large scale data that we have access to help us understand where a microhabitat might exist. Applying all of those into an algorithm, we can then validate with that training data and incorporate future climate predictions into the model. So this is what I am working on now. This is the next step. I finished creating this step here, and I am in the process of working towards this. And that's a really important step, right? That's the goal. This type of information can provide useful resources. My kind of tires are insulated, isn't that cool? Is great and interesting if you really like mosquitoes or really like tires, but it doesn't help public health or mosquito abatement policy. This type of work that can tell you exactly where these mosquitoes are likely to be for the next 100 years can actually impact policy, funding, and public health. So that's the long-term goal. I want to quickly make an acknowledgement about my work. So my work centered at field sites located in these 3 universities, right? These universities are all land-grant universities. Land-grant universities seized 11 million acres from 250 tribes in the 1800s to help fund them. In Wisconsin, we have over 1.3 million acres that were seized from indigenous tribes and used to fund land-grant universities. This isn't a past tense thing, this is a present tense thing. In 2019, $8.7 million were used from these land-grant seizures to fund the top 16 land-grant universities. The University of Wisconsin is one of those. In addition, in the state of Montana, the University of Montana does receive funds from these land-grant processes. So that's a good thing to be aware of. There's a really great article called Land-Grant Universities, which was written by High Country News. It has an interactive series of maps that let you see what indigenous lands fund what universities. I think it's a really good thing to take a chance and look at. In addition to that, I also want to acknowledge my funding sources, which is the Center of Excellence, the university lets me do my work, all of the partners that helped me get tires and monitor weather stations and collect mosquitoes, as well as the amazing people in my lab who did lots of work for me, my committee who supported me, and all the field site coordinators that let me stick cameras and tires in the middle of their study sites. With that, I believe it is time for questions. You can clap. It's okay. Please do. Yeah.
Have you looked at any variability with tire size and tire make?
Yeah, so I'm sure it exists. 100%. Have I looked at it? Absolutely not. That level of variability is way beyond the ability of any type of model to handle. I think it would be interesting, kind of like a trivia to know. I guess you could make a distribution to pull from randomly, but the fact of the matter is that that level of detail probably won't change the results of a model. But I'm sure it exists. It has to, right? Big tires have to do something different than little tires.
You could probably get some funding from one of the tire companies to demonstrate that their tire
Is-
is.
You know, that's I'll work on a sales pitch for that. I like it. They don't have to be mosquito-related questions. If you also have like I want to do something, how do I get there question, that's also okay, just so you know.
I have a question.
Yes.
So are you using, are tires a major source of breeding ground survival for these mosquitoes over the winter? So understanding the situation with tires would have a huge impact on the mosquito populations, or is this just a model to represent other microclimates that might be similar but not necessarily tires?
It honestly is both. So particularly for Aedes albopictus, for this Asian tiger mosquito, tires are critically important. If we go back through Wisconsin, Illinois, Indiana, Iowa, every single one of those initial establishments can be like drawn back to a tire center, to an initial introduction at tire centers. There also was an extensive amount of work done in the 80s and 90s that saw that movement of tires on interstates was the key driver in the dispersal of this mosquito. So for Aedes albopictus, the tire itself is critical. But I think it's not unreasonable to say that this is also a proxy for understanding other small microhabitats, because other habitats do exist. These are a container ovipositing mosquito. They will lay in any small space that contains water. And although they may not be equally as insulative, or they may be more insulative, it at least can give us some proxy of beginning to think at the correct scale. Yes?
Okay, so just following up on what you just said, if the tire distribution is reintroducing mosquitoes, does that happen every year? So in a sense, if they die out every winter, it wouldn't matter because they just get reintroduced by the tire.
Yeah, so there is some concern to that, right? There's this whole question of introduction versus establishment. Like, are we reintroducing tires, or are we establishing a thriving population? And what we see is initially, early on, absolutely, we're seeing these repeated introductions at these centers that are driven by tire movement. But what happens is that it may take a couple of years, but you start to see established populations. We've done, a partner of ours down in Illinois has done some genetic work looking at populations to see establishment. So looking at source origins and seeing when they kind of hit establishment. And we are seeing this shift in establishment, usually after like 3 to 4 subsequent emergence events, which may occur in the same year, right? There is some kind of other potential ecological factors as far as surrounding habitat that could influence that. But these really large tire recycling or tire management centers provide permanent habitat. So once they are introduced and reach this established population there, we are seeing it. Does that answer the question? Okay.
So would it be possible in northern climates to just simply in colder climates, just simply keeping tires covered? So they don't get snow covered?
Yeah,
Could
I
that
mean-
be an effective control?
Yeah, I mean, keeping tires covered or keeping water from it's like collecting in the
Collecting in them,
tires
yeah.
during the like ovipositing season. So that egg laying season would totally be potential controls. I think there's a problem of scale, right? Like maybe like a private landowner who maybe is storing their winter tires or their extra machine tires, maybe they can do that. But a tire distribution center or a large like Palms, which is like a commercial tire center, they likely lack the infrastructure or the willingness to invest in the infrastructure to do that. So then you run into like, okay, what kind of control efforts can we do? And there has been some work looking at how we can get controls into tires and into these spaces, which is a separate kind of set of work. Yes.
Did you think of incorporating a solar radiation pyrometers into your sample set?
Yeah. So I have solar data. I got it from those great weather stations. Illinois and Wisconsin and Michigan refused to use the same solar system, like solar monitoring systems, and I cannot get it to be calibrated correctly currently. I'm working on it. It's something I'm interested in to see what the level of solar radiation does. I think like solar radiation is fairly consistent at these sites because of the type of site they are. So I'm not sure even if I can get that data well calibrated.
If you were able to calibrate it, could you build it into an albedo effect to put it in your model as well?
Yes, I think so. Yeah. Again, I think that one of the things that, and this comes down to, this is the problem. This is the can of worms that is when you start doing these predictive modeling systems, is when is additional information useful and when does it start overfitting the models? When you start adding so many parameters or so many things you're worried about that you are becoming too specific to the exact system you're viewing that you can't extrapolate to new systems. And I think one of the problems with solar radiation data is that it is a lot of data, right? You have daily or sub-daily metrics. And it may, particularly because it's often very consistent at a single site, it's just going to effectively confuse the model because you have this extra term that's like, we're kind of the same, but everything else is changing. So it either won't explain variance and you kick it out, or it basically overfits your model because you have these small variances that it's trying to attribute to larger variances.
I'm bringing it up because we've seen higher inferences in water temperature, solar radiation over just ambient temperature because of just the radiation.
Totally. And I think one important thing about this system, which I at no point made clear, is that there is not standing water in these tires over winter. So we are truly just insulating the tire with these dried eggs adhered to it. So we don't, and not to say that there isn't solar radiation impacting the temperature of that tire, but we aren't working with water in the system. So it would likely still applies, but maybe in a slightly different way. Yes.
So you're looking at egg survival in the tires. Are you interested, or any other groups looking at that next life history stage?
Yes, there are. I am doing it too. It's just not in this. So I've done a couple of things working on that. So for a lot of that work, we actually shifted towards laboratory-based studies where we were able to more precisely control the tire experience. And then from that developed those through adult, and then wing size is a really well-established proximity for fecundity. So that involves pulling every left wing off of every mosquito that you've raised and adhering it to a slide and photographing it, and then putting it in a digital processing image and measuring it to 2 specific points to then see if there's an impact on fecundity. That it looks like it's early data for that still, but it looks like more stable conditions do increase fecundity. So not necessarily warmer, but more stable conditions increase fecundity, and the development rate. So time from hatch to adult is slightly faster in mosquitoes that are given a better chance to acclimatize to colder temperatures, which usually means that they have less stable conditions in fall. So it's a weird, I don't know what the conclusions are to that yet, but there's something there. I don't think a single student has asked a question yet. Yes.
Are there any other ecological factors that go into predicting this other than just for human transmitting disease?
So reasons we're interested in predicting it, or factors that are connected or associated with it?
Just what a mosquito, why are we trying to predict this other than for the...
Okay, yeah. So it really has to do with public health and quality of life. That's really the big thing, right? So they have the disease, you have the fact that they're really competent disease vectors, which is scary and can impact a lot of people. And like this mosquito specifically is mean. It really likes to bite. I have to work with these in the insectary, so you have to like clean the cages out. And you put your hand in there for like 30 seconds and you come out with like 45 bites. It's awful. They are mean and can be problematic. And so those are really why we care. There is another fact that mosquitoes are a small arthropod, so they're really sensitive to temperature. So they do kind of act as a warning species, right? They're going to respond the most quickly to changes in temperature of any type of species. So looking at mosquitoes can provide information maybe down the road for other hardier or slower changing or slower impacted species.
So there's no like effect on like livestock or wildlife?
Well, we do have not as much for Albopictus because of what it transmits, but for example, in some of our other mosquito species, you have Triple E and West Nile, which can both impact horses. So like in Illinois, Iowa, and Wisconsin, Triple E is mostly associated with equine mortality. So we do, like public health does work with veterinary partners to monitor Triple E in that particular mosquito. Yes.
So there's a lot of the shy pre-professional students in the room who may not appreciate what graduate school is really like.
Okay.
So I wonder if you could just maybe talk about why you chose to go to graduate school when you knew you wanted to go to graduate school.
Yeah.
How you got from UMW to research.
Yeah. So I think that is. I remember when I started thinking about if I wanted to go to graduate school, I would go up to graduate students and I would ask them, oh, how did you end up here? Like, how did you know this is what you wanted to do? Like, how did it all happen? And they would go, oh, well, it just all kind of worked out. And I was like, that is not helpful. I cannot do anything with it just worked out. So I think like for me personally, for my story, when I started at Western, I started thinking I was going to go to vet school, maybe med school. And it wasn't until, honestly, it was mostly through, I don't know if this is still true, but we had lots of literature reading assignments in our classes when I was here. And often through those, I started to gain this interest in this process of how we actually come to information. So by the time I was a senior, I had pretty much by the time I was a senior, I pretty much decided that doctor was cool, vet was interesting, but I was more interested in discovering new information. And I think that's the thing that's really cool about research. Research is constantly creative and constantly thinking. There's this really cool way kind of to visualize like being a graduate student or being like a PhD or being a researcher, right? Is you have all these concentric rings of knowledge. And as you get, all of us have roughly the same knowledge through high school, right? We all learn most of the same things. And then as you pick your major, it kind of starts to be a bubble, right? Where you don't study everything, you just study some things. And then if you do your master's, you get a smaller bubble that kind of sticks off of that. And then if you do your PhD, it makes this little tiny kind of finger point that reaches off at the end of that bubble. And the very tip of that finger, no one else knows, right? No one else has done what you do. No one else knows that piece of information. And so you are constantly having to be innovative and creative and thinking about what it is that you are doing and how that is the kind of a story that is yet to be told. And I found that really, really appealing. As far as getting from there, I guess, to here, because research hadn't been my main focus when I was here, I had very little research experience when I left Western. Which is frankly important for getting into graduate school. So I had to take some time to develop that. So I went down to the University of Utah and I took courses part-time and worked as a research assistant in a lab down there in protein ligation, making proteins. Not what I do now at all, but it gave me a taste for the research process. It also was a very young lab, so I got to see how these labs were developed. From that, I worked for biotech for 6 years. I worked again for a company in Salt Lake that did PCR based disease diagnostics. So they give you someone gives you a sample, you pound it up, you put it in a pouch, and an hour later it tells you what disease is in that sample, which is a really cool idea. And that is what got me thinking about big data and about diseases. From that, I went and did quantitative methods, right? The idea of how can I use big data to understand disease. And then when I started looking for a PhD, I was really lucky to stumble upon, when I say stumble upon, I mean I incessantly read papers in my field and kept reading papers by people I thought were interesting, right? That's what stumbled upon means. It means really actively searching the literature and continuing to read papers that you're interested in. And through that, I found this center and I found my PI and I found a field that I was interested in and reached out directly to be like, hey, I'm applying to this program. Can I come talk to you? And amazingly, she said yes. And then you have to go and convince them that you know what you're talking about when you have no idea what you're talking about, but it's about confidence, which is also what this is about. That was a very long-winded answer. I hope it was possibly helpful.
We'll see.
Yes.
Did you get your horse to Wisconsin?
No, I did not. I sold her in 2017. Yeah. 3 years of trying to convince her that running around barrels fast was a good idea was about all I had. For context, I was on the radio team here when I was here, so that was part of my experience here. Yeah. No, she runs high school and high school radio now and does really well. She's a very good pole bender. It turns out I was just doing the wrong sport.
You sent postcards to your horse?
No, that'd be a great idea though. I like all the Instagram posts with her in it though. Last call.
All right. Thank you very much, Katie. So he's going to be short real quick. Have to fill out and we get a $50 counter. It'll be well, other than you have to put it in the form and then Mary Dwyer, financial person.